So let's talk about an AC circuit containing just two components, and that's, in this case, we're going to consider that which has both a resistor, or that contains resistors and inductors. So we say RL series circuit, RS series circuit. So now consider an AC circuit this way, where we have a resistor like this, and then we have our inductor this way. There's an ammeter here, and then we have an AC source. It has both potential difference and frequency. So here is our resistor and here is our inductor. So now in this kind of AC circuit, we have where both of them are connected in series. In parallel, things could be different, but here in series we have now remember that in the resistor, in this resistor here, both the current and the voltage are in phase. That means they both reach their peak values at the same time. You see? Now, if we were to use a vector diagram to explain or to illustrate the relationship between these two quantities here, the current to the resistor and the voltage over the resistor, we have something like this. Because both of them are parallel, in phase, that means they'll be parallel. Their numerical value or their magnitude could be different, but the direction is the same. You see? Now, similarly, in the inductor, the voltage across the inductor leads the current in the inductor by 90 degrees or pi over 2 radians. And again, if we want to use vector diagram to illustrate this information, we'll have something like this, where the vertical axis will be the voltage across the inductor, and the horizontal axis will be current in the inductor. Of course, the phase difference will be 90 degrees, and that's the whole of this will be correct only if you take your reference point or your direction in this way. So here we call this the second diagram, vector diagram, and this is the first vector diagram. Now remember that since these two components are connected in series, in any series connection, it doesn't matter the kind of circuit it is. It could be a direct current circuit or an alternating current circuit like we have here. The current passing through every single component connected in series is the same, both in magnitude and direction. And that means that IR, as the current over the resistor, is the same as IL. As the current over the resistor through the resistor is the same thing as the current through the inductor. Now, since that's true, it means that this one here, we can replace the current passing through the inductor with the voltage in the resistor. So that means we have the diagram, the vector diagram 2 begins to look something like this. So where here is the voltage across the resistor, and here is the voltage across the inductor. You see, an experiment shows that both of them are out of phase by 90 degrees. You see, so since this is the we have the relationship between the voltage across the inductor and that across the resistor, and we know that the sum total of them will give us the voltage of the source. It means that we have to add the two of them together, you see. So here will be the voltage at the source. Now to find the voltage of the source, the potential difference of the source, we have, it's going to be a vector addition of these two. Now remember, if you have two vectors that are inclined with each other at 90 degrees perpendicular to one another, it means that their sum will be, we'll have to find their sum using the Pythagoras theorem. So we have V squared is equal to VR squared plus VL squared. We call this equation 1. Now remember that V is equal to IZ, of course, where Z is impedance in the circuit. And you know that VR is the voltage across the resistor. To find that using Ohm's law, we have I R, and then we have the voltage across the inductor. It becomes I inductive reactance, where XL is the inductive reactance. Is the inductive reactance. So we're going to put all these ones, equation 2 into equation 1. We put them, substitute their values, and so we have IZ squared is equal to IZ squared is equal to IR squared plus IXL squared, and that will give us I squared Z squared is equal to I square R squared plus I square XL squared. Now if you take a common factor, we'll get something like this. I squared Z squared is equal to I square R square plus XL squared. You see, so that equation now becomes, we have I's, okay, here, this can cancel this one out, so we now have Z squared is equal to R squared plus XL squared, and that means that, okay, therefore Z becomes the square root of R squared plus XL squared. So we call this equation 3. Now this equation here gives, equation 3 gives the impedance in an RC series circuit, sorry, RL circuit. So that's it. So in this kind of circuit where you have just these two components only, resistors and inductors, you know that in when the resistor, the current and the voltage are in phase, which is what we have here, in the inductor, the voltage leads the current by 90 degrees. Now you know that the current flowing through the resistor is the same thing as the current flowing through the inductor, because they are both connected in series. If they were connected in parallel, then different amounts of current will pass through them. Now, since that's the case, it means that VR will be in the same direction as the current in the inductor, and that means this vector diagram here, the second vector diagram, this is the first one here, and here is the second one. When you put them together, you will see that the voltage across the inductor will lead that over the resistor by 90 degrees. So when you find their sum, which is equal to the potential difference of the source, you know, their sum is going to be we can find that using Pythagoras theorem, and that gives us this, remember, from addition of vectors. So since V is equal to I Z from Ohm's law, these are all Ohm's law, we substitute all these values into this equation and make our Z subject to the formula. We get that Z will be equal to the square root of R squared plus XL squared.